This video came up on my Reddit feed. It's about the path that the Voyager 2 spaceship takes as we launch it into deep space. It's fantastic. It's a marvel of modern engineering. Obviously they did the math. What did they do? How did they figure out what path it was going to take? Well, they solved a kind of math problem that's called an initial value problem. The idea is, if I know all the forces acting on a particle, in this case, a spaceship, and I know the initial position and the initial velocity, then I can predict the future position of the particle. And it's great. I mean, in an academic setting, this is a really classic Calculus 3 math problem, but also it kind of hints at a bigger picture, which is that always a reasonable assumption to make? Is it always reasonable to assume that if you know all the forces acting on a particle and its initial position and its initial velocity, is it always fair to predict its future position? I want to do a Calculus 3 classroom level example where I work out the solution to an initial value problem. And also, I want to give you a tool so that you can start to build your intuition about what you can do in a situation where it isn't reasonable to assume that you can predict the future position of a particle if you know all of the forces acting on it and its initial conditions. Before we get started, I'd like to just remind you of the letters that we usually use when we're describing the motion of a particle in space. So usually we use r of t as the position of the particle, v of t, which is the derivative of the position, as the velocity, and a of t, which is the second derivative of the position, as the acceleration. I made up this initial value problem that is very academic and what you would expect to see on a Calculus 3 level test. It may not be very realistic, but I just want to give us a chance to practice pushing the symbols around on a page and seeing how the answer comes out. Here is the velocity of the particle at any time. Since F equals ma, this is equivalent to telling you all of the forces that are acting on the particle. Also, we have here the velocity at time 0 and the position at time 0. So what I need to do is a sequence of integrals to recover what the position is at any time. As a consequence of defining limits coordinate-wise, we know that derivatives happen coordinate-wise and integrals happen coordinate-wise. So what does that mean? That means if you are trying to integrate a vector that has functions in each of the coordinates, it really is as simple as just integrating each of the coordinates. So I'm going to do that calculation now. The antiderivative of 0 is just a constant, but since I'm going to have constants in each one of the coordinates, I'm just going to call this one C1, and then an antiderivative for 5e to the negative t will be negative 5e to the t plus another generic constant, and then an antiderivative for negative 32 will be negative 32t, and then I'm going to need one more generic constant out there in the z coordinate. So now we have a expression that tells us the velocity of the particle at any time. But it's got a lot of constants in it, so I'm going to use the initial conditions to recover those constants. So the velocity at time 0 is 7, negative 5, 2, and here is the velocity at any time. So what I can do is just plug in 0 anywhere there's a t in the velocity, and that must be equal to 7, negative 5, 2. So I'm going to do that now. So if I substitute a t in a 0 in for any of those t's, there aren't any, so I'll just have C1. 0 in for e to the negative t, e to the 0 is going to be 1. So this is going to be negative 5 plus c2. And then when you put a 0 in here for this, it's going to be negative 32 times 0. So I'm just going to get c3. And this gives us an equation. There's an equation in the x coordinates and an equation in the y coordinates and an equation in the z coordinates that lets me solve for all these constants. It's really tempting for students to just take this initial condition and literally just start substituting it in for the constants wherever you see them. But I want to be clear, that isn't the way that this works. What you need to do is take 0 and plug it in for all of the places that you see time, and then use that result to solve for the constants. Vectors are equal to each other when their coordinates are equal to each other. So this means that 7 must be equal to c1, and negative 5 must be equal to negative 5 plus c2. So I ended up with c1 is 7, c2 is 0, and c3 is 2. So what does this mean about the velocity at any time? We're getting closer here. So the velocity at any time will be c1, which is 7, negative 5 e to the negative t plus c2, which was 0, and then negative 32t plus c3, which was 2. So now I have the velocity at any time. One more integral, and we should be able to recover the position at any time. That shouldn't be so bad. So I need to do some antiderivative. So I'm getting the antiderivative of 7 will be 7t plus. Now I need some more arbitrary constants, and I'm just going to be a bit lazy here and just go ahead and use C1 and C2 and C3 again. Please understand that these are not the same C1 and C2 and C3 as when I was calculating the velocity, but they're just generic constants and they're about to go away. So I'm just gonna reuse the same letters. So now an antiderivative for negative 5 e to the negative t is going to circle back around and give me 5 e to the t plus, and then I'll need a c2 and the y coordinate, and then now in the z coordinate I'm getting negative 16t squared plus 2t plus c3. Okay, and then just like with the velocity, I'm going to now need to use the position at time 0, the initial position, to recover these constants right here. So r of 0 is 3, 6, 10. So this means that 7 times 0 plus c1 must equal 3. So c1 equals 3. Now likewise here in the c2, in that y coordinate there, I'm getting e to the negative t, and I'm plugging in 0 for t, so I'm going to get 6 is equal to 5 plus c2, so I'm getting c2 is equal to 1. And then in the last coordinate here, when you plug in 0, all of these t's are going to go away, so I'm just going to have c3 and 10. So that's it, c3 equals 10. And that's it, we've done it. We have solved this initial value problem. Let me write the answer here. It isn't so bad, just kind of on the academic level, just on the classroom, how hard is this question going to be on a test? I don't think it's so bad. You just take a sequence of antiderivatives. Really, the only pitfall is forgetting to plug in the initial time so that you can actually get some equations that let you solve for the constant. So usually students do pretty well on this. I have this result here graphed in CalcPlot 3D, so you can actually see the path that we calculated. Okay, and so here's what I did to make this path. All I did was I inserted a space curve and then just used the answer that we worked out. So it's kind of nice. You can actually have CalcPlot 3D animate this particle moving along the path as well. So, based on our forces acting on this particle and our initial conditions, this is going to be the path that this particle must take. This conclusion can be a little bit misleading because it seems to be what I'm saying is that if you tell me the initial condition and the forces acting on a particle, then I can predict the position of this particle at any time. But that's missing out on a crucial assumption about the way that the world really works, which is how precisely can we measure the initial position and initial velocity. So what I'm going to do is I'm going to insert a vector field, and I really like CalcPlot3D's default vector field for this example, so I'm just going to use their default vector field. They use pretty colors, but I just want to have a constant primary color. So I'm imagining the force acting on a particle as being variable and depending on the position that that particle is in space. And then, according to our results here, all you need to do is tell me the initial conditions and I can predict the path that the particle takes. So let's do it. The computer will do it for us. Actually, if you just click on a place in this plane, then the computer will plot the future movement of the particle. So let's go ahead and do that. So if I click right here, you can see that these vectors in the fourth quadrant are pretty strong. So they kind of push it off in this direction. And then apparently over here, it kind of gets pushed back towards this spot and then sort of spirals down here in the middle. So that's interesting. If you drop the particle right here, if those are the initial conditions, then the particle ends up sort of getting caught in this kind of whirlpool up there. So let's look. Actually, there's a lot of different places that I can drop this particle. Any of these initial conditions will result in the particle kind of getting caught in this sort of whirlpool and always end up in that same spot. But let's suppose that I move the particle closer and closer and closer to the y-axis. Then right here, all of a sudden, when I move the particle onto this side of the y-axis, the particle ends up in a completely different place. There's this scene in Jurassic Park where the math nerd is explaining that if you drop a droplet of water on your hand, then depending right on where you drop it, it could go in completely different directions. So that's what he's trying to explain here. This is called sensitive dependence on initial conditions. So one of the prerequisites for solving problems in this way is to make sure that your initial conditions aren't close to a place like this. We call it a bifurcation point, where if you change your initial conditions just a little bit, then you end up with a very different result. So that actually paints a much scarier picture than the kind of nice world that we were viewing a minute ago, where so long as you tell me the force and the initial conditions, I can predict the position of the particle. Because, if our particle is close to one of these bifurcation points, then a slight imprecision, just measuring the initial position of the particle barely wrong, could actually mean that our predicted result and the result from reality are very, very different. So that's kind of scary. How can we guard against this? And in what way can we hope to understand these kind of force fields that have this happen? That's a really big question, though. How can we understand all of the different complicated kinds of force fields? So what I want you to do is focus on the most basic kind. That is where whatever goes in the x-coordinate is just some constant times x plus some constant times y. And likewise, what goes in the y-coordinate is just simple multiples of x and multiples of y. There's a lot of interesting behavior that can be captured in just these very simple kind of vector fields. And I have one here. You can see it's 0.12x minus y, and then here's the other coordinate, and this is what it looks like. So this is kind of cool. It has this sort of spiral behavior. And you can see here, if I drop a particle in this, the computer's just run out of time here. It would keep spiraling inwards and inwards and inwards. So that's interesting. I was able to use a very simple one of these vector fields and create this kind of spiral nature at the origin. So what you can do is you can actually just input this generic vector field as I have, and if you use A and B and C and D, then CalcPlot 3D will interpret those as sliders, and you can play around with these sliders and look at all of the different vector fields that you can produce. It's interesting. Gosh, I wonder what would happen if you dropped particles in this vector field here. So it's kind of, it's not immediately obvious to me what happens as you play with these sliders, but I will tell you that there's a lot of depth in this question, and having intuition about the way that this graph behaves and the kinds of graphs that you can produce is going to play a big role in the kind of math that you're going to study after Calculus 3. So it's probably worth your time to just, open CalcPlot 3D and, generate this vector field that I use here and just kind of play with these sliders, and just sort of start to see all of the different pictures that you can create. Is it possible for you to maybe make one that where everything just moved in a perfect circle? Could you do that? It is kind of a bummer that, see here, I'm starting to get some of that spiral behavior, right? Whoa, let me bring this one down. Okay, could you start to mess with it to the point that you got a perfect circle? Unfortunately, you can't just drop a particle in this. If you have sliders, then the computer won't interpret it correctly. So you have to just write down what numbers you were using, and then, like what I did, make another one and then put those numbers in there. So I really think it's worth your time to go in there and play around with those sliders and enjoy the pretty pictures that math can make.